After learning about the functional groups, let's talk about the alkyl halides and alcohols and then amines, because we need to know about their types also. Similar to what we had for carbons and hydrogens, let's say if we have a group Z, which can be halogen X or OH. So this is X when you have alkyl halide and OH when you have alcohol. Okay? It can be OH or X. So how to determine the type of alkyl halide or alcohol based on, again, the type of carbon that these functional groups are attached to. So if OH is attached to a carbon which is primary, the alkyl halide and the alcohol is going to be primary, or the same for alkyl halide. If they are connected to a secondary carbon, they're going to be secondary alkyl halide or alcohol. And if they are connected to a tertiary carbon, then they are considered a tertiary alkyl halide or alcohol. The practice on page 6, we're working on A. We're supposed to determine the type of alcohol. So we pay attention that OH, make sure this is not carbon, this is O, right? This is the connection to O. This carbon that is connected to OH is connected to one more carbon. So this is a primary carbon, and the whole alcohol is considered a primary alkyl halide. Let's work on B, and then I will leave C and D for you. Fluorine is connected to this carbon, right? And this carbon is connected to 1, 2, and 3 other carbons. It's a tertiary carbon, so the whole alkyl halide is going to be a tertiary alkyl halide. Can you classify OH or halogens in the next one? Just pay attention to the carbon and you will get it. Okay, about the amines or amines and amides. Okay, we have combination of carbon and nitrogen in amines and combination of carbonyl and nitrogen in amides. So for amines, if carbon and nitrogen are connected this way, means nitrogen is connected to one more carbon, it's a primary amine. If nitrogen is connected to two carbons, you see for amines it's slightly different from alcohols and alkyl halides. So when nitrogen is connected to two carbons, it's called a secondary amine. And when nitrogen is connected to three carbons, it's called a tertiary amine. Same thing for amides. We said amides are a combination of carbonyl and nitrogen. So when nitrogen is connected to one carbon, it's called a primary amide. When nitrogen is connected to two carbons, besides the carbonyl is connected to one more carbon, it's called a secondary amide. And finally, when nitrogen is connected to three carbons, it's going to be a tertiary amide. So these are the types of amides and amides, alkyl halides and alcohols that we wanted you to know at this point. I'm not going to work on all the practices on page 7. Dolastatine, the big compound is too big to draw, and I'm sure you can do the amides and amides and primary and secondary. what the question is asking. Identify amines, amides, and sp3 carbons as primary, secondary, or tertiary. First of all, this first one is when you have combination of carbon and nitrogen is an amine, right? What type of amine is it? Nitrogen is connected to only one carbon, so it's primary. Here we have carbonyl and nitrogen, so it's an amide, right? What type of amide is it? Nitrogen connected to two carbons, so it's a secondary amide. Amide because of the carbonyl. And we are supposed to determine the type of the sp3 carbon. sp3 carbon, whenever you have 4 groups around the carbon. So carbons that are double bonded are not sp3, they are sp2. These and these are sp2 carbons. So the rest of the carbons are sp3, this one. And the type is carbon is connected to 2 carbons, so this is secondary. This carbon is connected to 2 more, this is another secondary. This carbon connected to 2 more, so this is another secondary. And this carbon is connected to no carbons, just the oxygen, so you do not determine its type. This carbon is connected to 2 more carbons, this is another secondary, and each of these carbons are sp2 because of the double bond, so you cannot consider them as sp3. Okay. Alright, the next practice on page 7. We are supposed to draw a structure of a compound that fits the descriptions in the question. First, an aldehyde with the molecular formula C5H10O. So, I hope at this point you have a little bit of more knowledge about functional groups. So, when we say an aldehyde, means that our functional group is this. We're talking about an aldehyde. So, out of 5 carbons, one of them is spent in the functional group. Oxygen is spent here, and out of 10 hydrogens is spent there. So let's build the rest of the molecule. We need how many more carbons? 4 more carbons. So let's put carbons first. 1, 2, 3, 4. So total of 1, 2, 3, 4, 5. Well, we have spent our oxygen. We need how many more hydrogens? 10 minus 1, 9 more. And we are supposed to complete the octet on each carbon. Now let's double check if we have 10 hydrogens. 3, 5, 7, 9, 10. So this is a formula for aldehyde. So you can easily write it as CH3, CH2 instead of these lines. I just wanted you to see how I complete the octet. Then CH2, CH2, and that's it. B. A ketone with this formula. So what was the difference between ketone and aldehyde? Aldehyde is RCOH and ketone is RCOR. So means that we need to have CO in between and some carbons on the on 2 sides. So it doesn't matter how many carbons you want to on each side. We just are looking for a very general formula. So again, we use the oxygen and one of the carbons. So let's go for 10 hydrogens and 4 more carbons. Doesn't matter where you put them. C and C, and let's put C and C. So we have 1, 2, 3, 4, 5. Spent 5 carbons and 1 oxygen. It's time to complete the octet. using 10 hydrogens. How many more bonds do we need around this? 2. So we have a CH2. How many bonds we need around this carbon? 3. So we have a CH3. And the same story on the other side. Count. 3 and 2, 5. 3 and 2, 5. 5 and 5, 10. So that's the formula. So for C, which we're looking for an ester with this formula C5H10O2, it's the formula for an ester is RCOOR. So put COO. Doesn't matter where you put on these sides. We have used one of these carbons and both of the oxygens. So just keep it simple here, CH3 only. And how many more carbons do you need? 3 more. C, C, C. If we don't put these hydrogens here, how many hydrogens do we need? 10. This carbon has only one bond with oxygen, so it needs 3. This carbon needs only one bond with the carbon because it already has 3. This carbon has 2 bonds, so it needs 2 hydrogens. Same here, and the last one needs 3. So let's double check the hydrogens. 3, 5, 7, and 10. And finally D for a carboxylic acid with this formula. You see these are all isomers, but different functional groups, different arrangements. So you can say for carboxylic acid you have COOH at the end. So we use both of the oxygens. We need 4 more carbons and 9 more hydrogens. 1, 2, 3, and 4. The end needs 3, CH2, CH2, and CH2. So 3, 5, 7, 9, and 10. So all the atoms match. One more thing we need to work on about the functional groups, and it's important for us, besides being responsible for the reactions and functions in the a molecule, functional groups also are responsible for the amount of the melting point, the boiling point, the solubility. So we need to have a very quick review on intermolecular forces that you had in general chemistry too. Intermolecular forces. Intermolecular forces exist between the two molecules, intermolecular. And we had 3 types of them. We had London forces that you can find in all molecules. But between nonpolar molecules, you can find only London forces, like between 2 CH4 molecules. Because both of them are nonpolar, you just find the very weak London forces. London forces are very weak. The second intermolecular force, a little bit stronger than London forces, are dipole-dipole interactions. Dipole-dipole interactions are only between the molecules with dipole, only between polar molecules. Like, let's say you have CHCl3 and HBr. So CHCl3, if we draw its Lewis structure, the dipole is towards chlorine, so it's a polar molecule. It's highly partially positive. This is partially negative here. So the there is a dipole-dipole interaction between the positive and negative sides of the molecules. And finally, hydrogen bond, which is the most important of them, is between hydrogen and these three, F, O, and the three most electronegative elements. So hydrogen of one molecule and fluorine, oxygen, or nitrogen of another molecule, like let's say between water. Some of my examples are non-organic, inorganic, okay? And let's say you have CH3F. So between fluorine and hydrogen, you have a hydrogen bond. And between these hydrogens and oxygen. So hydrogen bond is the strongest. And what is the relation between the intermolecular forces and the melting point, the boiling point, and the solubility? The higher intermolecular forces, the higher boiling point and melting point, mostly boiling point, and solubility, which we will look at them in the next few pages. So the higher the intermolecular forces, like the molecules with hydrogen bonding, they will show higher solubility and higher boiling point if they're in the liquid form. And also for the solids, we will have a higher melting point. All right, so let's just work on a couple examples on page 9. We are supposed to determine the type of intermolecular forces. Let's determine it for nicotine molecules, since it's a small molecule and it's easy to draw. Between the two nicotine molecules, let's find out what are the intermolecular forces. So as soon as you see nitrogen will form a, and we have hydrogens here, right? And also hydrogen there. So between nitrogen and hydrogens, you will have hydrogen bond. Didn't we say hydrogen bond forms between hydrogen of one molecule and fluorine, oxygen, or nitrogen of another molecule? Or between nitrogen and these hydrogens also. There is no limit. They can form these interactions between any of the two atoms. Between the two aromatic compounds, carbon and hydrogens only the nonpolar bonds, so we just have London forces. Or if you want to say between nitrogen and carbon, you will have a dipole, because the bonds are polar, right? This is partially negative, and this is partially positive. So between partially positive and partially negative, you have the dipole. For also, we do it for vanillin, and you will be responsible for aspartame. Alright, as soon as you see O and H, they are big signs of hydrogen bonding. So see between hydrogen and oxygen's hydrogen bond. The same oxygen and hydrogen here. Between the two aromatic compounds, London forces. Between the oxygen and carbons, you see dipole. Between Oxygen and carbon also, you see dipole, dipole. So this is a very good molecule to have all of these, to show all of these intermolecular forces. So that's how you can work on aspartame. The last practice on page 9, still working on page 9. It says, what type of interactions are present in these molecules? I'm assuming by in these molecules means between the two molecules of the same type. So for a compound which is composed of just carbon and hydrogen, the only intermolecular force is weak London force because it's not polar. There is no dipole-dipole. We don't see fluorine, oxygen, or nitrogen, so there is no hydrogen bond. For C, for example, you see a nitrogen, right? So between this nitrogen and hydrogen of another molecule, you will definitely have the hydrogen bond. And for, if we say for D, you see Cl. Cl makes a bond because it's electronegative, partially negative. This side is partially positive. So with another molecule of the same type, with another dipole, we will have dipole-dipole. You can work on the rest. Now, we just said the higher the stronger the intermolecular forces, the higher the boiling point. On page 10, we are looking at the boiling point. Let's say you have a pure sample of an alkene, just alkene by itself. When you start boiling it, if you pay attention to the intermolecular forces, you just have London forces. So it makes this, it's very weak, right? But London forces are the weakest. So when you have weak intermolecular forces, the molecules start releasing each other faster, and molecules can escape to the gaseous phase faster and easier. That's the description for boiling, right? Escaping the molecules from liquid phase to the gaseous phase. So the weaker these intermolecular forces, the molecules are easy to release. The same for alkyne and aromatic compound. Another one with different intermolecular force is an alkyl halide. You see, for alkyl halide, halogens are more electronegative. They make the bond polar, so between carbon and halogens, we have dipole-dipole. So if you compare the boiling point of an alkene and an alkene halide, you will see, besides the London forces, because we said London forces exist in every single molecule, like between every single molecule, every two molecules, because you always find the nonpolar parts to have the London force together. But here, besides the London force, we have dipole-dipole. So we expect the boiling point of an alkyl halide, average alkyl halide, to be higher than an alkene. If we talk about alcohol, what do you see here? Besides the London forces between carbon and carbon, what do you see? Here you have London forces. What do you see, which is very eye-catching? Hydrogen bond. So if you try to boil some alcohol, it shows the highest boiling point of all of these three. The same as what we talked about here, you can work on the rest of them in the table. On page 11, look at some general trends for the boiling points. The stronger the intermolecular forces, the higher the boiling point. That's what we said. The largest the surface area, the higher the boiling point. We're going to talk about it here now. We are going to determine if this one has a higher boiling point or How many carbons does each one have? 1, 2, 3, 4, 5, and 6. Here, 1, 2, 3, 4, 5, and 6. Both of them contains 6 carbons, but what is the difference? This one is more spread. This one has a larger surface area, right? So between the two molecules, with the one with the larger surface area has the larger boiling point because it has larger London forces. Okay, so it has a higher boiling point. And between C and D, can you tell me between C and D which one is higher? I'm sure you would say this one because of the formation of hydrogen bond. You have more polarizable atoms. Also in this next practice, let's see. For C, for example. This one or this one. If you said this one has higher boiling point, you were right, you got it right. Why? Because it's a larger molecule, higher surface area, and two more bonds here versus one more bond here. And for B, okay. Which one do you think? If you said this one is correct because of the hydrogen bonding in this area. And you can rank the next one in the order of increasing boiling point. Which one will have the highest boiling point between A, B, and C? I'm not going to draw the structures. The video is going to be too long. Between A and B and C, A has the hydrogen bonding. C has hydrogen bonding a little bit. It does not have hydrogens in it, but dipole-dipole. And this one, B, has only London forces. So which one has the highest? A with hydrogen bond, then C, and then B. For melting point, the trend is similar to boiling point with the higher intermolecular forces, and also we need to consider the symmetry of the molecule. Okay. The next thing is the solubility. The trend of solubility and the boiling point is the same. The higher the intermolecular forces, the stronger the intermolecular forces, the higher the solubility of compound. So, here, you see all the bonds are nonpolar, right? So, there is not much to react with. There is no oxygen or hydrogen in the alkene molecule to form the hydrogen bond with water. So mainly we have London forces or maximum some dipole-dipole interactions. So it keeps the solubility low. If you do this experiment on an alkene, you will see the solubility is low. You will see the two layers for the two liquids, water and alkene. But if you do it with an alcohol, you will see you have lots of opportunities for hydrogen bonding. And we all know that alcohols are very soluble in water. If you work on a nitrile, let's work on a different molecule today, this time. you see like hydrogen bonding between oxygen and between hydrogen and nitrogen, another hydrogen with nitrogen, the dipole, these are hydrogen bonds. The dipoles between oxygen and carbon, so it makes them pretty soluble. You won't see two layers, you will see one layer. So that's how you determine the solubility. Moving towards page 13. Which compounds are expected to be soluble in water? Again, just go with the possibility of formation of hydrogen bond. If you see the oxygen, it can form the hydrogen bond with water. So this one is soluble. If you have this compound with water, this is nonpolar, so it's just London forces, so this is insoluble. And the same for whenever you have oxygen and nitrogen, basically you have the soluble compound. Now let's go towards the table on page 30, comparing the solubility of alkanes. You see, going from butane to pentane to decane, boiling point increase, so you expect the solubility to be more and more. So you see, for butane, it's insoluble, right? For pentane, is a little bit more soluble. It might not be visible if you do it in test tube, but still we see insolubility. And for decane, you will see more solubility. Maybe you see one phase this time. So as the carbon chain gets longer, the boiling point increases a little bit, increasing chain. Boiling point increases because of the surface area, because the London forces are going to increase. The second table, table 2, this was table 1. Table 2, it's comparing the solubility of 3 different alcohols, methanol, ethanol, and propanol. With increasing the length of the chain, you see the boiling point increases, and the solubility is the least for methanol because that's the smallest. The chain is not that long also, although they have the OH group for the hydrogen bond. The ethanol is more soluble and propanol is infinite solubility. You can add as much as you want. So that's how the solubility of alcohols changes. And the third table is about branching between pentane, 1, 2, 3, 4, 5. This is pentane. It's insoluble. Boiling point is 36. Isopentane, boiling point is 28. Isopentane is 1, 2, 3, 4, and this is the isopentane. We talk about how to name these alkanes later in the next chapter, so don't worry if you don't know them yet. And for neopentane is this. So we still can say the solubility is insoluble, and you see by branching they all have 5 carbons, by branching more, the solubility and boiling point decrease because of less surface area, less London forces. More branching, boiling point, and of course the solubility decrease. The trend for boiling point and solubility is the same. Table 4. Between one ethane, between an alkane, insoluble, ethanol, infinite, and 1, 2, 3, 4 is butanol. Butanol is 7.9 per 100. So you see, by increasing the chain, going from ethanol to butanol, the solubility decreases. This is something weird that you see for the alcohols, because by increasing the chain, the number of carbons and flowing the electrons plays a role. So it's not like by increasing the chain of alcohols you can dissolve as much as you want. No, there is a limit, and the number of carbons plays a role for alcohols. Okay, let's work quickly on some of these. Circle the molecule that should have the higher boiling point. We're looking for higher boiling point, so we have to look for the stronger intermolecular forces, CH3OH or CH3SH. Which one has the possibility for hydrogen bonding? This one. If we talk about CH3OCH3 or CH3CH2OH, which one has a possibility of hydrogen bond? This one. So between CH3CH2 or CH3CH2CH3, which one? The longer chain, more intermolecular forces. Between butane and isobutane, what is the difference? Isobutane has more branches, right? So the solubility decreases. Between CH3CH2OH or CH2OH, CH2OH, which one? You have two sites for hydrogen bonding versus just one. So this one has higher boiling point for sure. Can you talk about the solubility in water now between ethanol and butanol? You just saw in table 4 that ethanol has higher solubility. Between ethanol or ethanoic acid, this is ethanol, and this is ethanoic acid or acetic acid. Because of the existence of CO and OH, this is more polarized, so ethanoic acid has a little bit higher solubility. Work on this compound CH3 versus an OH. I am sure by now, whenever you see oxygen, you will pay attention to the hydrogen bond. Now let's see which one of these. This time I'm just working on one to see which one is more soluble in hexane. Don't forget, like dissolves like. We are talking about hexane. Hexane is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. It's the nonpolar molecule, right? Like dissolves like. Polar in polar, nonpolar in nonpolar. So this time we're looking for a nonpolar molecule because it has to dissolve in a nonpolar solvent. Propanol or propane. This is propanol and this is propane. I'm sure you would say this one because this is a nonpolar molecule. work on the next one, see which one is more soluble in a hexane. Okay, this video is very long, but I have to finish it with a little more about functional group. So at the beginning of this video, I told you that the functional groups are responsible for reactivity of the compound and function of the molecule. So for example, let's say if you have this alkyl halide, this is an electronegative element, so it's a partially negative side and it makes the carbon partially positive. Or if you have OH somewhere, oxygen is partially negative and the carbon is partially positive. And you remember oxygens and nitrogens with the lone pair of electron act as Lewis bases, right? So it's time to introduce electrophile, means electron lover. Likes electron. So has a positive or partially positive charge. That's why it loves electrons. And another term is nucleophile, nucleus lover. Or positive charge. So it has a negative or partially negative charge, means basically full of electrons. So you see both of them are full of electrons. You see the non-bonding electron pairs. So we name both of them as nucleophiles. So the sign for electrophile is E, the sign for nucleophile is Nu. Now in the reactions, the attack or the flow of electrons is always from nucleophile towards electrophile. Like for example, as soon as we start the alkenes chapter, you will see that this is a nucleophile because this is full of electrons, so it's going to the electrons move from nucleophile to electrophile. Or when we have this, then nucleophile is going to go to the carbon and the bond opens. So what way we will have them. A little bit more of practice here and we will have to finish this video. We'll work on the first one. We'll label the electrophilic and nucleophilic site in each molecule. Partially negative because of its electronegativity, so carbon is partially positive. So this is going to be nucleophilic, this side is going to be electrophilic. I'll work on B, leave C for you. We said wherever is full of electrons is nucleophile, so double bond is always a good nucleophile. And again, sulfur is has electrons, so is nucleophile, or you can say this is electronegative, partially negative, and makes carbons around it partially positive. And the last practice, considering only electron densities, state whether the following reactions will occur. If you predict reaction, use arrows to indicate the attack of nucleophile to the electrophile. Alright, so I do it for A. We say here is partially negative, carbon is partially positive, and we have an OH. So let's determine the nucleophile and electrophile first. Which one is full of electrons? nucleophile is OH. And which one is has a positive charge or partially positive charge? This one. So it's going to go from here to here. And B, full of electrons, is a nucleophile, plus bromide, again full of electrons, nucleophile. Does this reaction happen? Nope, it's not going to happen. No reaction. Do it for C and D. If you have any questions, let me know.